Yes, up to now we have seen different fabrication steps one by one. So at the first topic we have seen the crystal growth. Okay, so in that crystal growth, what we have done is we have a raw silicon material into that. Okay, into that a silicon wafer basically we have designed, we have you can say fabricated. So we have silicon dioxide, or we call it a sand. We have sand. By using the crystal growth techniques, by using this crystal growth techniques, we have obtained the wafer. This is done by this crystal growth method. After that we have gone for epitextual growth. Okay, so in this epitextual growth, what we have done is we have a wafer. So wafer we have grown with the previous step, that is crystal growth. Once we have got the wafer, in that we have grown a layer of a layer of the same material. Suppose it is of silicon, so the same silicon layer we have grown, so this is called EP layer. That layer we have grown, that is called EP layer. The next process, next step that we have seen is the next step we have seen the oxidation. So once we have a wafer, and in that wafer we have this same material. On the wafer we have epitextual layer. On this EP layer we have grown oxide layer. So in oxidation we have basically grown an oxide layer. So this is SiO2. Okay, so till now we have seen. Next step that comes basically in fabrication, that is available in fabrication, is basically the lithography. Basically we call it photolithography. So in photolithography what we do is, this is the complete structure up to oxidation. We will be removing this selected part of SiO2. So for our, suppose for CMOS, or we call it NMOS or PMOS deposition, we need and this oxidation. So here okay, so this was the same silicon layer. Okay, onto this we have this oxide. So with photolithography what we do is we pattern this oxide. As the oxide is throughout this substrate, or we call it wafer, we will be shaping this SiO2 to our required uh, area. What area, in what area we are going to fabricate the NMOS or PMOS, in that area only we will be requiring your oxide. So by using photolithography we only left with this part of SiO2, all others will be removed. So this is done by photolithography or lithography. It is a method called lithography. And after that, after this lithography, it comes the diffusion. Okay, So in diffusion, what we will be doing is in this region, in the channel region, we will be basically depositing the N type or P type based on this diffusion we will be making. So if it is P type substrate is there, we will be making N type diffusion to have an NMOS basically. Okay, so N plus diffusion we require. So this deposition of this source and drain basically layer is basically done by the diffusion. In this lecture, we will basically see the diffusion process. So till now, we have not seen this lithography. We have studied lithography. This lithography will comes after this diffusion. So considered here like after lithography, this was the structure we will be obtaining. So we have assumed like we have this structure, and on this we are going to perform diffusion. Okay, so this type of structure will be there without this diffusion region. Only this structure. In this, we will this diffusion layer basically. Okay, so here, so what happens in diffusion basically is diffusion means there will be it is diffusion takes place when there is a high concentration region is there and a low concentration region is there. So it is suppose it is higher concentration region is there, and this is lower concentration region is there. So if any charge carrier concentration or any atoms, suppose there are higher atoms available here. Okay, suppose there are higher atoms of a particular uh, element. Okay, so suppose here less concentration is there. So if there is a concentration gradient, then there will be a diffusion taking place from higher to lower concentration. Okay, so in crystals or wafers that we have fabricated, on that wafer we have seen different type of defects. We have seen different type of defects: point defect, area volume defect. Okay, so there are different type of. So with respect to this defect, there will be some space available in the crystal. So this is the crystal. Inside this there will be some defect. So in that defect, whatever concentration will be there, defect is nothing but the vacancies, some available spaces. Okay, so this defect will be having low concentration of the impurity atom. Okay, and outside this there will be high concentration of impurity atoms. So basically we are going to perform the doping here. Okay, so that means we are having higher concentration of impurities outside than the impurities inside the crystal. There inside the crystal we are having less concentration of the impurities. So there will be a concentration gradient. So there will be a change in concentration. So as there will be a change in concentration, there will be the chance of taking the there because of this concentration gradient. So this concentration gradient will be because of the availability of defects. So why there is diffusion will be taking place only because there is some defects available into the crystal. So some defects are available into the crystal. So how much crystal defects are available here? If it is higher defects are available, that means more spaces will be available to accommodate outer atoms, or you can say dopants, or we call it impurities. So if the crystal is having available spaces in the form of interstitial space or substitution spaces, so that defects will basically cause a place for the impurities available there. So because of, or we call it due to the availability of defects in the crystal, there will be a process of diffusion. The diffusion process will be taking place into this crystal or wafer because of this uh, availability of the defects. Okay, so we will see the definition of uh, diffusion. So before that, we will see like in silicon is having a crystal structure of diamond. It is having a diamond crystal structure. So in that diamond crystal structure, it has been observed like it has 34% of occupied spaces. That means whatever shape of this silicon will be there, out of that 34% is the only space occupied by the silicon atoms. Okay, so all other space 6%, so 66% space is, you can say, free to occupy or free, or it is a free space, or uh, in between the atoms the space is called interstitial, so we call it so it is interstitial spaces. Okay, so this silicon structure having diamond shape, diamond crystal structure. So diamond crystal structure is having 34% occupied space and the remaining 66% at the interstitial space that is free to be occupied. Okay, so these spaces are basically used for diffusion. Okay, so there will be a movement of uh, impurity atoms from high concentration to a lower concentration. So in terms of diffusion, we can define this diffusion as the atomic movement. It will be atomic movement. So it is the atomic movement of dopant impurities, or we call it diffusant. Okay, so dopant impurities or diffusant through vacancies. So when there is a defect available into the silicon crystal, or we call it a vacancy or a space, so these vacancies will be causing the movement of dopant atoms. Okay, so these vacancies will be in the form of interstitial spaces. Interstitial spaces. Okay, so these interstitial spaces will be making sure like the movement of dopant atoms will be taking place through these interstitial spaces or vacancies that is available in regular crystal lattice. So in the regular crystal lattice, whatever vacancies or spaces are available, in between these spaces and vacancies, the movement of this impurity, dopant impurities or diffusant will be causing this diffusion process. Okay, so basically the diffusion okay, so this diffusion is defined with respect to different type of impurities available into the crystal. So if the impurity available is of the type substitutional, or we have seen in point defect, we have seen a type of defect that is called substitution defect. So in substitution defect, what was there is suppose these are the silicon atoms. Okay, there will be some vacancies. So instead of these atoms, there will be some impurities. So some vacancies will be available. So this is like a regular crystal structure. So here some vacancies are there. So these vacancies will be occupied by the impurity atom, and these impurity atom will be moving from one available vacancy to another available vacancy. So this uh, defect is called substitution. This moment is basically called substitution. It has substituted the silicon space available for silicon. It has been substituted by the impurity. So this is impurity atom, and this one is silicon atom. Okay, so again here also vacancy is there. So this impurity atom will be moving between the available spaces. So this is called substitution vacancy. So this is one type of diffusion. So based on the substitution defect, there will be a diffusion. Okay, another one is interstitial. So there are interstitial spaces available. So suppose this is the regular crystal structure of silicon. Silicon atoms are placed like that. So in between these atoms, there is these spaces are called interstitial. Between two atoms, whatever spaces are available, that is called interstitial space. So in these interstitial spaces, the impurity atoms will be available. So these impurity atoms will be available into this interstitial spaces, and the movement will be taking place. So this is called diffusion because of interstitial space available. Okay. The third one is called interstitial C. So interstitial CI we call it. Okay. So first one is because of substitution defect. Another one is interstitial. Another next one is interstitial C. Okay. So these are different type of diffusion based on the defects available. Okay. So this type of diffusion is called interstitial C diffusion. So in that interstitial C diffusion, what is there is there will be a regular silicon atoms placed. Okay. So into that, suppose this is the silicon atom, and there will be an impurity, and what it will do is in interstitial C, the impurity will be available at interstitial space, but it will force the silicon atom to move into the interstitial space, and it will occupy the silicon space by the impurity atom. So impurity atom will push this silicon atom available into the crystal, and it will push this silicon atom into the interstitial space, and the silicon atom space will be occupied by the impurity atom. So this is called interstitial C, because impurity was available in the interstitial space, and it is going to replace the silicon atom. So that this is called this your interstitial C. Okay. So in interstitial, the dopants are available in the interstitial space only. Okay. It is not going to replace any silicon atom available in the crystal. It is occupying only the interstitial space. But in interstitial C, the impurity atom available in the interstitial space is going to remove the silicon atom available at the crystal in the crystal, and it will be occupied by the impurity atom, and the silicon atom will be pushed to the interstitial space. This is called interstitial C. So these are different you can say types of diffusion. Okay, so we will see some examples with respect to these. Okay, so in case of substitution method of diffusion, the examples here are phosphorus, arsenic, and antimony. Okay, so these are the different type of dopant that shows the nature of substitutional diffusion. Okay, so these diffusion these dopant atoms will be showing this substitution type of diffusion. Okay, so here so basically these substitution type of diffusants, phosphorus, arsenic, and antimony, basically these are pentavalent. Okay, so basically these are pentavalent. If it is pentavalent, once it will be replacing the silicon, so there will be an extra okay, so there will be some extra electron will be there with respect to this. So because it is pentavalent, so four outer electrons will be forming a bond with the adjacent silicon atom. One extra electron will be available. So these are pentavalent, so it will be having an extra electron. This extra electron will be helpful for electrical conduction. Okay, so basically electrical conduction, or we call it electronic movement. So basically it will be helpful for electronic movement. So this is example of this phosphorus, arsenic, and antimony is the example of substitution diffusion. The next one is interstitial diffusion. So in interstitial diffusion, the elements of group 1 and group 8 of the periodic table, these are group first and group 8 elements, shows the property of interstitial diffusion. So the example here is lithium, sodium, helium, and argon. So these are the different elements of group 1 and group 8, shows the interstitial type of diffusion. Here in this case we can see, even if the crystal is not having any defect, because the crystal is pure, it is not having any defect, then also these type of elements can reside inside the interstitial space available to make the movement of this atoms basically. So the diffusion can be taking place because of the availability of spaces available in the interstitial space. Okay, so it does not basically does not require a vacancy, or we call it defect, or we can have does not require a vacancy. Okay, so it does not require any vacancy to make this type of interstitial diffusion. Okay, in this interstitial diffusion, it has a subclass like in this type of cases there is a type like sometimes it shows both nature. So this interstitial is having a subclass. So in that subclass, we call it subclass is interstitial can show substitution as well as interstitial. So another type of diffusion is there. In that it will be showing substitution type of diffusion as well as the interstitial type of diffusion. So in this is shown by basically the elements that are called like copper, nickel, uh, gold. So these are the elements that show the combined substitution as well as interstitial type of diffusion. But basically it is a type considered to be a type of interstitial type of diffusion. Why? Because this substitution type of diffusion basically is of very slow nature. It is of very slow nature. So this type of diffusion very slow, but interstitial type of diffusion is fast, very fast. Okay. So if any type of diffusion is there that is having substitution as well as interstitial type of method, then overall this interstitial type of diffusion will be superseding this substitution type of diffusion because it is of slow nature. So overall the diffusion will be taking place is because of the interstitial only. So there is a type of diffusion that combines the substitutional defect as well as the interstitial defect. So by using this to combine the type of defect is there that comes under the interstitial only, because interstitial is more, you can say, influential with respect to the substitution because it is faster. Then this diffusion because of substitution method suppresses basically becomes negligible, so it comes under the interstitial type of diffusion only. So the example of these type of elements that show both type, that is combined nature of substitution and interstitial type of diffusion, is called copper, nickel and gold. Okay. In case of interstitial type of interstitial C, in terms of interstitial C type of diffusion, here also, like initially the element was the atom was available in the interstitial space, it has replaced or substituted the silicon, and this silicon atom will be available into the interstitial. This is called interstitial C. The example of this interstitial C is given by like the boron. So boron is a type of diffusant or the dopant that shows a nature of interstitiality type of diffusion. Okay, so this is the only p-type diffusant that shows this interstitiality method type of diffusion. Okay, so there are these are the different type of diffusion we have seen. The next we will see basically the laws that governs these diffusion. So we will see some laws that governs this diffusion. So one of the laws that we will be following here is called Fick's law. So there are two different laws of Fick's, that is first law and second law. Okay, so Fick's law is given by the scientist Fick's. Okay, so here it basically says, we will see the first one, the first law of Fick's law. Okay, so by using this Fick's says that the in case of a one-dimensional movement, so the movements that we have seen here is this impurity atom is basically moving in one direction only. So either it is moving in this direction or this only. It is not moving in multi-directional dimension. It is having a movement in only one direction. So this is called 1D movement. Okay, one-dimensional movement. So if the diffusion of atoms, impurity atoms, are taking place in one dimension, then this has been explained by this Fick's law. Okay, so Fick's law only depicts the one-dimensional movement of dopant atoms. Okay, so basically it governs, it says one-dimensional movement of, it says one-dimensional movement of dopant. Okay, okay, so it is one-dimensional movement of dopants in diffusion process basically. So it is a type of process where diffusion process where we are considering only the one-dimensional movement of dopant. So this has been assumed in case of defining the Fick's law. Okay. So the first law of Fick's says like this is J. This is called the flux. This is called the flux basically. So flux is like a structure is there. So suppose this is a silicon structure is there. Okay, so this is the silicon structure, and here two different planes have been defined. Suppose two different planes have been defined. Okay, and suppose these are two different planes. This is P1 and this is P2. So this is the silicon substrate or silicon structure crystal is there. Into this, we have defined two different planes, and the movement, the diffusion has been taking place in this direction, and this distance, two planes have been separated by a distance called dx. Okay, so two planes we have taken. So how much or what is the concentration of dopants crossing one plane, okay, and the concentration of P2 crossing the other plane? So these is defined by the flux. Okay, so what is the flux is basically the concentration of dopant. Suppose it is N1 and this is the concentration at P2 plane is N2. So the difference divided by this dx, that is considered to be the flux. Okay, so this flux is basically defined as minus a d del n by del x. Okay, so here d is your diffusion constant, we have already seen in the previous lecture also, and n here is basically this n defines the concentration of dopant. So n defined concentration of dopant. So this n defines the concentration of dopant, and this x defined this dx is the distance between these two planes, that you can say incremental distance we call it. So from plane 1 to plane 2 there is a distance, and this basically explains the flux. So this flux is given by J is equals to minus d del n by del x. Okay, so this is called the first law of Fick. Okay, so this is Fick's first law. Okay, so here this basically valid, this fixed first law is basically valid in case of like we are having diluted solution, or we call it this basically holds, or this basically valid for diluted solution, or we call it, that is diluted solution means there is less concentration of dopant is available. If there is less concentration of dopant is there, then this is called a diluted solution. So this is basically we are considering very less concentration of dopant. So initially we are considering, like, with respect to the crystal concentration, the silicon atom concentration, the concentration of dopants are very less. Then in that case this holds valid. Okay, so here we are going to have the analysis of diffusion in one dimensional. The movement of dopants are in one dimension only, and the concentration of dopants are very much less with respect to the concentration of the silicon or the crystal structure. Okay, crystal atoms are there, so it is considered to be a diluted solution. Okay, so this relation, the flux, is basically given by minus d del n by del x. That is considered as the first law of fix, or we call it the fix first law. Okay, it explains the flux basically. Okay, and here we have seen the diffusion. So this diffusion constant, previously we have seen this also, like diffusion constant is given by exponential minus ea divided by kt. So here this ea is the called activation energy. Activation energy of diffusion. Okay, so this is the minimum energy must be required to make sure diffusion starts. So okay, this is our diffusion activation energy. So with respect to this, we have seen, like, the activation energy in case of substitution type of diffusion is very high considered to the activation energy of interstitial type of diffusion. Okay, so this is the case. For example, it is around 3 to 4 electron volt in case of substitution type of diffusion. But in case of interstitial type of diffusion, the activation energy required is around 0.6 to 1.2 electron volt only. That means the activation energy in case of interstitial is very less compared to the activation energy required for the substitution type of diffusion. So by using these two, we can conclude, like, the diffusion in case of substitution type of diffusion process or method, the diffusion constant value will be very less with respect to the diffusion constant value in case of interstitial type of diffusion. So what does it indicate? It indicates, like, if diffusion is high interstitial type of diffusion, that means if higher diffusion constant is there, that means there will be higher flux will be there. Okay, a higher, so that means there will be more dopants passing through these planes. Okay, in case of interstitial type of diffusion, that means there will be uh, a nature, the diffusion type, that is interstitial type. This interstitial type diffusion will be faster because there are large number of dopants are passing through this plane in case of interstitial type of diffusion, then that will be a faster type of diffusion that we have seen previously. So it is being governed by this formula, that is first law of Fick's. Okay. Next we will see the second law. Okay, so the second law is defined in terms of rate of change of dopant atoms. Okay, so basically the rate of change of dopant atoms, if we consider that, that will be del n divided by del t. So this is the rate of change of dopant atoms. So this is a rate of change of dopant atoms. So if we are going to multiply this del n by del t with respect to the cross sectional area of the crystal into the dx, that is the volume. So we are going to multiply this volume with respect to rate of change of the dopant, that will be considered as the rate of accumulation of dopant atoms between P1 and P2 planes. So here, so we are considering the rate of change of these two uh, dopants available between these two planes. So whatever the dopants are available between these two planes, or we call it between the volume available between the two planes, that will be called like that much of dopants are going to accumulate. Okay, or that is accumulate we call it, or they are going to diffuse. So okay, so this is like the number of, this is del n is the change in the concentration of dopant into the particular volume that we have taken between two planes with respect to the time. So it is a rate of, basically it is considered as the rate of accumulation. If there is this much of concentration of dopants have changed their concentration between this volume with t time, with respect to this t time, then that will be considered as the rate of accumulation. Okay, so this is rate of accumulation of dopants between these two planes. Okay, so this rate of accumulation of these dopant between these two planes will be considered as, will be equals to change in the flux density. Okay, so in the, by using the first law of uh, Fick's, we have seen how the flux is defined. Okay, so that flux have been defined by the first law, and with respect to that flux, if we consider, so this rate of accumulation of dopants will be equals to the flux change in flux density. So the flux was defined by J, so the flux density will be defined as area multiplied by the change in J, that is change in flux density, sorry, the change in flux. So this change in flux is, suppose at x the distance the flux was Jx minus the change, that will be the flux at x plus delta x distance. So this is change in flux. So this is change in flux multiplied by the area, that will be flux density, basically what is the flux available. So now we can define delta n divided by delta t will be considered as, if we say it it will be J x plus dx minus jx. This a and a will be cancelled out, so it will be dx. So this is the relation. If we take the limit, okay, so if we take like limit dx tends to 0, so basically we are going to take the limit to this equation like dx tends to 0, it is dx. So if we are going to take this limit, then it will be converted like delta n divided by delta t is equals to minus of delta j divided by delta x. Okay, so this has been converted to a incremental change in density divided by delta x. Okay, so this is coming out to be the equation. So with respect to the first law, and by using this we can see here delta n divided by delta t is equals to, if we consider, we put the value of j from the equation first law of physics, then it will be coming out to be del x del divided by del x into d del n divided by del x. Okay, this is Fick's second law. So what here what does this indicate is basically these two law basically governs the one-dimensional movement of the dopant into the crystal. So we will see the advantage of these two laws that is being defined. So these two laws are basically going to govern the one-dimensional movement of dopants. So with respect to these two laws of Fick's, we will see how the concentration of this dopants basically going to affect the diffusibility or diffusion constant, or how this diffusion constant is going to affect the diffusion of particular atoms to the silicon crystal. We will see that into the next class.